I'm back in the classroom. It was hard to finish that last one because people came and you guys couldn't hear, but they were talking to me and talking around me. And I was like, trying to do a video, peeps. Anyhow, so we're still talking about the greenhouse gases. We just finished, let's take a look. We just finished talking about CO2, right? And CO2 emissions. And then we are going to be talking about nitrous oxide. Somehow a little box came up around oh, there, got it. All right, so we're going to talk about nitrous oxide. Nitrous oxide is actually scarce. It's 1/1000th as abundant as CO2, but it is also very effective at trapping heat. So it is 300 times more powerful as trapping CO2. And since we're talking about all the ways that we are impacting our system and kind of overloading this system with human behavior, we figured that we should just throw this one in here. If you notice the picture behind this information, may look unfamiliar to you unless your parents garden or if you've ever like spent any time on a farm. This is a fertilizer. This is because we do produce high amounts of fertilizer, and nitrogen is something that's needed. We learned about in macromolecules, right? Nitrogen is essential for proteins and for deoxyribonucleic acid, DNA, and other nucleic acids, aka ATP. So we need nitrogen. Nitrogen, I think we talked about a little bit, is very inaccessible. Like you can breathe it in, you can breathe it out. It's 78% of the atmosphere, but it is in a form that we cannot get to biologically. Whereas nitrous oxide is a little different. But nitrous oxide is a gas. It is. Don't be breathing this in. If you know, you know, and if you don't, that's you can look it up, but don't mess with that. Nitrous oxide comes from typically from combustion or use of fertilizer or feedlots, it comes from industrial resources. 1/3 of emissions of nitrous oxide are not natural. So yes, a forest fire or volcanic eruption, it can produce nitrous oxide, but most of what we're seeing coming into our atmosphere is actually because we're doing this. It has a long atmospheric lifetime, so it will not break down. CO2 is going to, it can eventually be absorbed by living organisms and photosynthesized back into the systems, or it might dissolve into the ocean. Nitrous oxide, not so much. So you can see that nitrous oxide concentrations, they are not related to, other than they can be produced through the combustion of fossil fuels. So alongside CO2, they can be produced. But when we're looking at fertilizer, it's not necessarily related, or if we're looking at feedlots, it's not necessarily related to the other greenhouse gases of the production. It just happens to be that in all of our awesome human endeavors trying to feed the world, we do produce a lot of fertilizing agents, and with that comes emissions of nitrous oxide. So we're seeing that increase as well. All right. The big one. Well, I think this one is an issue that we aren't talking enough about. So methane actually has a warming effect that is 21 times greater than CO2 per molecule. But then as you get more methane, it actually increases. So it's 58 times greater per pound. So if there's a lot of methane in an area, the heating in that particular area is actually exponential. Concentrations have increased since the industrial age, 8 times faster than CO2. 700 parts per billion was in the atmosphere before the Industrial Revolution. But then now we're at 1,700 plus parts per billion, which was measured back in 1998. So I know that's actually increased from here. The atmospheric lifespan is about 9 to 10 years. It takes about a decade for that methane to break down. One of the things that is really concerning is with our large agricultural processes and the decay of foods. If we create a lot of food now, and then we have decomposition, or the accumulation of trash. When we put our trash in landfills, it one of the byproducts of that is methane. Methane is natural gas, basically. It can come out of the ground. It's something we pull out of the ground for fossil fuels, but it's also something that gets produced through a lot of industrial processes, agriculture, and there are ways to capture it, but we don't always utilize those. And one of the big threats is the thawing of areas of permafrost. And so we see increasing atmospheric methane concentrations that are just going right alongside the nitrous oxide and the CO2. Because methane is frozen in so many places and held in the ground in our polar regions. As those regions begin to thaw, one of the big fears is that methane will really be something to combat, because it does stick around for a really long time, and it is a really powerful agent that we talked about, this positive feedback loop. The danger with methane is that it can create a positive feedback loop of warming. The more warming, the more methane released. That creates more warming, creates more methane released, because of the vast areas that are frozen and are beginning to warm. Another greenhouse gas that we need to talk about is halocarbons, and what we really want to talk about here relates more to the damage done to the ozone layer. So I think in this there's a video. I'm not going to be able to play it on here, but it will be linked, so you need to get in and find that video and watch the video on the whole hydrocarbon and ozone story. So ozone, what ozone is, I think we'll go into that a little bit here, but we know that halocarbons were synthetic compounds that were used for really good things, but the consequences, so we got good technology, but then the consequences of CFCs became apparent, and we realized propellants and solvents and cleaners and coolants and things that were stable, that weren't catching on fire and doing crazy damage, there was damage that we weren't seeing immediately. So in 1987, the Montreal Protocol you'll see a collective that actually banned substances that would deplete the ozone layer. And we've got some good news regarding that. But nearly all of the halocarbons were a result of human activity, almost all of them. They are produced in volcanoes. We keep talking about volcanoes, but they are. But for the most part, it's human activity that's putting these in high concentrations into the atmosphere. Atmospheric concentrations between atmospheric concentrations of halocarbon are between 0.2 and 16.5 parts per trillion. Their warming effect is 3,000 to 13,000 times greater than CO2. But the thing about this is we don't really know when they break down. They're very stable, and they will interact with ozone. And when they are exposed to UV or particular conditions in the atmosphere, they do weird things. So we've learned a lot about them. We know that they are not good for the overall atmospheric health and for our environment. And so we have combated those. So you can see CFCs are not a good thing at all. So watch this video. You're going to see it will be linked within the day. And this one's really informative about the story, and just kind of like the scientific discovery of something. Here's the thing about science. We only know so much, and we're still discovering things. And sometimes when we learn something, it's not politically convenient. The Montreal Protocol is an example of when politics and economy seemed to have an answer outside of what was already being produced. And so they listened, and there were changes. And now there's good things that have happened because of it. It doesn't always go this way. It definitely isn't going this way with climate change. All right. So we know that ozone, you watched your video. I'm assuming you watch the one on Montreal Protocol, but we understand the importance of the ozone layer now. The stratospheric ozone layer forms in the stratosphere, right? It is a natural formation. The tropospheric ozone is a greenhouse gas. It does increase heat. Oh, you can't see that. Let's see if I put it right in front of me. Okay, remember this little guy right there? So this is temperature. That's temperature. And you can see that as you are, like if you could travel up there and you're traveling through the stratosphere, that temperature increases as you're approaching the tropopause, or the stratopause, sorry, between the mesosphere and the stratosphere. And so the temperature is increasing because the ultraviolet rays are being absorbed by the ozone layer, and they are actually heating up. And that area up there, it does, heat, like heat can transfer, right? And so there is some transfer of heat from that. It forms when nitrous oxide reacts in the presence of sunlight or lightning in the atmosphere. And so we do get some surface level when we have nitrous oxide being produced through the combustion of like fossil fuels. Ozone can actually form just because of electrical activity. So surface level ozone is toxic, but the stratospheric ozone is necessary. Half of tropospheric ozone, something about coming from human activities. I have to look that one up. I'm not really sure what that point was there. But the atmospheric lifetime of ozone is actually really fast. So it's a very unstable molecule, and it will break apart and create oxygen again really, really quickly and easily. Ozone can actually be used, because of its toxicity, it can actually be used to sanitize. And because it breaks down really quickly again, it's pretty safe. But you shouldn't breathe it. It's not good for you. All right. So all this to say, Earth's climate has fluctuated a lot over its 5 billion year history. Some of these fluctuations have been very different than what our current temperatures are. However, these changes have occurred slowly over thousands of years. And we know that it's really about averages long term. And the average temperature has increased by approximately 1 to 2 degrees Fahrenheit, which is between 1 and 1.8 over the last 100 years. And maybe even a little more over the last 150. So many of the world's leading climatologists feel that greenhouse gases and human production of those are a major cause of global climate change. Within the last 650,000 years, the CO2 level has never been higher than it is. It's never been higher than approximately 370 parts per million in a natural state, and we're at 390 parts per million. The temperature correlates very directly with this. So we do have proxy data. We have ice cores and things like that do show that when CO2 levels go up, so does temperature. And when CO2 levels rise extremely high, we do see an increase in methane production. And methane production can actually bring about really large, we have evidence of like large extinction events happening because of methane production. So wanted to kind of take a look at this. The year 2023 was the warmest year since global records began in 1850. We have 1.18 degrees that we are above in 2023, or above the global average, or the 20th century average of surface temperature, which is okay. I want you to understand that this is a global effort. This is a coordinated scientific effort to gather data, and that there's not really a good political motivator or economic motivator for creating like a chicken little scary, like, hey, the world is warming, that really, this is the accumulation of data, just basic surface temperature that has been measured and compiled into a composite view of worldwide average surface temperature over the last 100 and over 150 years. So we really do need to look at the data and see that things are changing. And so that's it on greenhouse gases. I hope you learned something new. Make sure that you watch the videos that are assigned to you so they give you a better picture of everything that's going on. Have a great day, and I shall see you tomorrow.